Okay, so the plan today, finish the last little bit of 3.2% applications and start and hopefully complete 3.3 solving mixture applications. I posted a few more sections of homework up, so you should see a few more sections available now on WebAssign. The quote of the day today is that one physical test is worth 1,000 expert opinions. So, um, particularly in the so-called hard sciences, the sciences that are strongly experimental based, so like physics, chemistry, uh, in areas like maybe parts of engineering, things like that. Um, it doesn't matter how beautiful the theory is or how elegant it is or how much it seems like it ought to be true, or and it doesn't matter, you know, what the credibility is of the person saying it if the theory disagrees with the practical evidence, the experimental evidence, then the theory is what's wrong. So now, of course, there are caveats to that. Uh, we have models that are wrong but are quite useful, and we say, okay, they're not perfect, but if I wanted a better model, it would be much more complicated. I'd rather have the simpler model and deal with the slight inaccuracy or something. So not really talking about those kind of trade-offs that we actively choose, but the just talking about the value of a physical test of actual experiment in science. And kind of in that vein, so I'm on a committee, a general education committee with our philosophy professor, Drew Van Land, and he is offering a new philosophy course this coming fall. The details aren't set yet. We don't even have the schedule for fall set yet. So college wide. So this is just kind of putting it on your radar in case anybody happens to be interested. Um, but as of right now, we offer two philosophy courses. I think it's 101, just intro to philosophy, and 105, I think is the number, logic. I think those are the only two we offer. And so he's putting this new course out there, Philosophy of Science, and it looks like a really interesting course. I saw a preview of the syllabus, and uh, and it talks about things like, what's the difference between science versus what we might call something like pseudoscience, right? Um, so what is the difference in the types of arguments or the types of data they present or the way that they present that data? How can we look at an argument and say we think this is a scientific argument versus a non-scientific argument? What are maybe the limits of science, right? Not all questions can be answered with scientific arguments and scientific analysis. So looking at things like that, I think it'll be a really interesting course. So if anybody is looking um, for something to kind of fill in a slot in your schedule. Maybe keep an eye out for Philosophy 206. Seems like an interesting course, and it's uh, sometimes it can be tough to get a course to run the first semester that it is put on the schedule. We just need enough students to sign up for it to get the sections to run. So if this sounds like something you're interested in, particularly in today's world, trying to just being bombarded with information and trying to sort out the kind of wheat from the chaff, this might be an interesting course. All right. So we're going to start with solving percent applications. Uh, I just posted or pasted our steps here again to remind us of what our steps are in these word problems. 'Cause I know that word problems are an area that some folks find challenging. You know, word problems are a bit of a double-edged sword. On one hand, it's nice because we have some context. It's a little bit more fun to read and solve a problem like this than to read and solve a problem like some of the ones we were doing last time. Just what number is 40% of 270 or something. Um, and we have other benefits in that we have a context that we can check our answer against. In this case, we have units, although the units aren't going to really come into play too much here, but we do have units to check against. So it gives us a little bit more material that we can check our answer against. Certainly if we got a negative number for something like what's the total recommended daily amount of sodium, we would suspect that that's not correct. But on the other hand, given that more context, that means we have to be a little more diligent and careful about plucking out the information and arranging it in the correct way. So we're gonna, like usual, do kind of one example and then do one exercise. So let's take a look at this first example. So let's first read through it. A grilled chicken salad at a popular fast food restaurant contains 630 milligrams of sodium, which is 27% of the recommended daily amount. So if you look on the nutrition label on probably just about any food, you can see, how much sodium it has and what the percent of the RDA is. What's the total recommended daily amount in milligrams of sodium? So what if we wanted to reverse engineer from that nutrition label what we think the total amount of recommended sodium intake per day is? Okay, so read the problem, identify what we're looking for. The question at the end is, what is the total recommended daily amount in milligrams of sodium? So let's just call this S. I suppose if we wanted to be nerdy, we could call it N for Na for sodium, for natrium, the Latin name for sodium, where Na comes from on the periodic table, but we'll call it S for sodium because that's a little more straightforward. So S will be the total recommended daily amount of sodium. That's what we're looking for. And we gave it a name. So I guess I did steps 2 and 3 together. Now we got to translate into an equation. And we might be tempted to do something like S equals 27% of 630, but that's not really what we have here, right? Let's be careful. Let me use a different color for this. 630 milligrams of sodium, which is 27% of the RDA. So it kind of looks like we have an is here, which usually denotes equals, and I think here it does, right? I'm saying that one thing, 630 milligrams of sodium, is the same as another thing, 27% of the recommended daily amount of sodium. One of the things that's being equated, one of the phrases is 630 milligrams of sodium. So this is 630 with a unit of milligrams, which I'll just kind of note down here below the equation. So that little milligram is not like a subscript or anything like that. I'm just kind of noting it off to the side here. And that's got to be the same as 27% of the recommended daily amount. So that's got to be the same as 27% of or times S. Now 27% is unitless and S is in milligrams. The recommended daily amount in milligrams of sodium. So we do have milligrams times the unitless quantity equals milligrams. Our units check out. If we had made some kind of mistake and we got something like 630 S equals 0.27, we'd have milligrams times milligrams equals unitless. And that wouldn't seem right. So checking units is just another way to check that we have things kind of lined up properly. And in fact, you can take this even a step or two further. I think this treads into dangerous territory, but some people actually, teach this, but they use what they call dimensional analysis, which is actually using what you know about the units to set up the equation or to set up, a proportion or something like that. Personally, I think that's giving the units a little bit too much center stage. I think we want to set up the equation based on fundamental principles and then use the units as a check. But some people do talk about dimensional analysis, essentially using the units to come up with the equation or expression that you're interested in. But our units check. So we are looking to solve now the equation 630 equals 27% S, or 630 equals 0.27 times S. And hey, now we just have a linear equation of one variable. Number times variable equals number. We've isolated the variable term. We need to isolate the variable itself by dividing by the coefficient. 0.27. So we have 630 over 0.27, or so I need two more decimal points, or two more decimal places on top to move that decimal point two to the right down below. So 63,000 over 27. And I know that 9 times 7 is 63, so this would be 9 times 7,000 to make 63,000 over 9 times 3 is 27. So 7,000 over 3. And what can I think? What can I think about 7,000? Well, that's like 6,000, which 3 goes into nicely. And then 1,000, maybe that's like 900 plus 100. So 600 or 6,000 plus 1,000. And I can split that 1,000 into 900 plus 100. And then I know that 100 over 3 is about 33. 6,000 over 3 is 2,000. 900 over 3 is 300. And 100 over 3 is 33.3 repeating. Or so we have a recommended daily amount of a little over 2,300 milligrams of sodium, or a little over 2.3 grams of sodium, if you wanted to think of it that way. Any questions on that? Okay, so I think the challenging parts are, one, extracting the information carefully and properly. Um, two, just being really careful with all of the details, our units, making sure that we get just, kind of the simple stuff like moving the decimal point the right amount of places, things like that. And then three, just being careful with our answer. Is this a sensible answer? Can I see that 27% of 2,300, or say about a third of, something like 2,300 is 630? Yeah, that seems like a sensible statement to make, right? So checking my answer, but really extracting the information from the text, and then just being really careful about the details, especially in this case, say like being careful with that decimal point, handling that properly. I think those are maybe the two challenging parts of this problem. Okay, so as an exercise, maybe take about 4 minutes or so and work on this one. So according to an article from Time Magazine, annual global seafood consumption rose from 22 pounds per person in the 1960s to 38 pounds per person in 2011. Find the percent increase. So what's the percent increase from 22 to 38? So we'll take probably about 3.5 minutes for this one, and then we'll come back and discuss the answer. Okay, let's talk about the answer. So I didn't see any questions in chat, so hopefully that is a good indication that that folks feel pretty comfortable with this problem. But if you do have any questions, you know, just a reminder, you can always pop it in the chat, or if you have questions as we go along here, you can unmute and ask. So we have a percent increase problem. Now that means we need to recall a formula, and every once in a while, there are some formulas from previous material, either previous material, say in this course at some point, or in previous courses that we just need to know. The way we get percent increase, and I put this up about 45 seconds or so uh, after after we started working on the problem. So if you were stuck, you could have referred back. But the percent increase formula is the new amount minus the old amount, all divided by the old amount, or it's the change in amount divided by the kind of original or the old amount. So we have a percent increase that we're looking for going from 22 pounds per person to 38 pounds per person. So the new amount is 38 pounds per person. The old amount is 22 pounds per person. So our percent increase is 38 minus 22 in the numerator, all divided by 22 in the denominator. Note that everything is denominated in pounds. So I have 38 pounds minus 22 pounds. Subtraction makes sense because I have the same units. I really can't subtract numbers that have different units. It doesn't make sense to say, what is 38 pounds minus 27 seconds? That just doesn't make sense as a question to ask or as a statement to make or something. But if I say 38 pounds minus 22 pounds, I'm kind of comparing apples to apples, so to speak. I can do that addition or subtraction. I can divide or multiply, for that matter, different units. So it does make sense to say I traveled 20 meters in 10 seconds. How many meters per second did I travel? That is actually a sensible thing to do. So we can multiply and divide different units, but we can't really add and subtract different units. Of course, if we had, it would be an example like, 38 pounds minus 10 kilograms or something. And as long as you're not, too into physics or anything, and it doesn't bother you that I'm comparing weight and mass, we can convert kilograms to pounds, and you can convert like that, of course. But fundamentally different units, we can't add or subtract. But in this case, we see we have pounds minus pounds. Everything is good to go. 38 minus 22 gives me 16 in the numerator. I simplify the numerator first. When I look at this, I think of 38 minus 22 as being like it was in parentheses before divided by sign. So that's really what I'm kind of thinking of here, just in case you were a little confused on the order of operations there. The kind of whole numerator is thought of as basically being in its own parentheses, and if needed, the denominator would also be considered as basically being inside of its own set of parentheses as well. Of course, with the 22 here, we don't really need another set of parentheses, but we get 38 minus 22 is 16, and then just bring the denominator over. Note our units in the numerator are pounds, same units in the denominator. Our units actually cancel out, they go away, pounds over pounds. So we end up with a unitless quantity. And that's exactly what we want with a percent increase. And 16 over 22, I can divide a factor of 2 out of the top and bottom to get 8 over 11 as my fractional form. Or I can type 8 over 11 or 16 over 22 for that matter into a calculator. And I see I get about a 73% increase. So not quite double, a little less than double. Any questions on this? Little side note, I'm going to draw this in red, not for any particular reason. It's not bad, but just to use a different color. Well, let me come down from up there. Some folks prefer to think of percent increase as new over old minus 1, basically just splitting up this fraction and doing, noting that old amount over old amount is just equal to 1. So just a little aside on that, there's, if you wanted to do the problem using this formula, there's nothing wrong with this formula. It's exactly the same formula. We're just splitting up this numerator into new amount over old amount minus old amount over old amount, and old amount over old amount just makes a 1. Uh, so just a little side note there. Any questions on 3.2% applications? Okay, so let's move on then to 3.3, solving mixture applications. All right, let's start with, I sometimes think these problems are a little bit silly, these like coins problems, and apparently now we're getting rid of the pennies, so we might have to even change up our coins problems more, who knows. But if we look at a problem like this, I think it's a good model because it's very tangible. And when we get to more abstract models that might be a little more, or abstract applications that might be a little more realistic, they tend to be a little less tangible, a little more going on. So these make nice models. I don't know anybody who actually has ever needed to solve this particular problem, but it's a nice model for problems that people do need to solve, but that just have a little more going on. So what's the question here? Well, Carolyn has $2.55 in her purse, combined in nickels and dimes. The number of nickels is 9 less than 3 times the number of dimes. Find the number of each type of coin. So we have a mixture here. We know something about the total mixture. The mixture of nickels and dimes has a total value of $2.55. And we know something about each component's role in the mixture. The number of nickels is 9 less than 3 times the number of dimes. So like, who doesn't know the number of nickels and the number of dimes, but they know that the number of nickels is 9 less than 3 times, right? So it's a little bit of a contrived problem, but again, we're using this more as a model for this type of application. All right, we need to define the number of each type of coin. That is our goal. So let's give our types of coins names. Let's let n be the number of nickels, and let's let d be the number of dimes. So these are what we're looking to solve for, to find. And I have 2 pieces of information about these nickels and dimes. If you kind of recall that I mentioned briefly last time that if we have 2 variables that we're looking to solve for, we have 2 what we might call degrees of freedom, that if I just told you somebody has some nickels and dimes, you could kind of pick the number of nickels and the number of dimes any way you want. Each of these is a constraint. So if I say, well, but their number of nickels and dimes, that they have to add up to $2.55 in value, that places a constraint on how many nickels and dimes there can be. You can't have 10,000 nickels now, right? So I have one constraint and I have a second constraint. So if I know that I have 2 variables that I'm looking to solve for, in the back of my mind, I'm thinking, okay, I'm probably going to be looking for 2 constraints. I'm probably going to be looking for 2 separate equations to come out of this paragraph of text. So I have 2 variables. So I'm expecting 2 equations. Okay, well, one equation is pretty obvious. I suppose they're both fairly obvious, but one of them is really easy to write down. The number of nickels is 9 less than 3 times the number of dimes. That's saying that 2 quantities are the same, so that is translates to equals. Well, the number of nickels is just n. And then we have this other phrase, 9 less than 3 times the number of dimes. So if I had 9 less than 12 dimes or something like that, well, 9 less than 12 would be like 12 minus 9. So I need something minus 9. That's what 9 less than means. This bit means something minus 9. What am I subtracting 9 from? 3 times the number of dimes. Or in other words, it's 3D minus 9. So the number of nickels n is equal to 9 less than something minus 9, 3 times the number of dimes, 3D. That's my one constraint equation. The other one we might get a little tripped up if we're not careful. So let's be careful with this one. Carolyn has $2.55 in her purse in nickels and dimes. We don't see an explicit is or anything like that, or a plus or something like that. But we do know that the total value of the nickels and dimes has to be $2.55. We might be tempted to do something like this if we were, moving a little too quickly. But really, we have to be a little bit careful, right? $2.55 that's denominated in dollars. If I just did like nickels plus dimes, these are unitless. Just number of nickels is a number like 3 or 5 or something. It has no units. Same with number of dimes. I would see that the right-hand side is unitless, but my left-hand side is in dollars. Or again, if I was being not too careful, I might say, well, each nickel is worth 5 cents, so maybe I have 5N, and each dime is worth 10 cents, so 10D. This might seem a little more reasonable, but 5N, what does that represent? If I have 1 nickel, 5N represents 5 cents. This right-hand side actually represents the number of cents that I have, while the left-hand side is representing the number of dollars. I don't have the same units. So I do actually have to be fairly careful with my units here. So there's kind of, this would be a correct equation, provided that we respect the fact that we have different units on the two sides and we fix the units before we proceed forward. So what do I want to do with this? I can go either of two different ways. I can turn the right-hand side into dollars. Each nickel is worth 5 cents, or that's $0.05. And each dime is worth 10 cents, or that's $0.1 times the number of dimes. If we convert everything into dollars, I mean, this is a valid equation. We could go forward from here, but I have decimal points all over the place. I think what I would rather do is convert the left side into cents. $2.55 is 255 cents. And then my right side can just stay the same. So I think these are the two equations I want to work with. Again, and would it be wrong to use the blue equation phrased in terms of dollars? No, but you probably end up multiplying both sides by 100 anyway to clear the decimals. But my two equations now are n equals 3D minus 9 and 255 equals 5n plus 10d. And what I'm going to be looking for here is to plug one variable into the other equation. So in one hand, I know that 255 equals 5n plus 10d, but I know that n is the same thing as 3d minus 9 by my first equation. So I have the 255 equals 5n, or that's 5 times 3d minus 9. I better make sure that entire 3d minus 9 that I'm swapping in for the n, that whole thing needs to be multiplied by the 5. So I put parentheses around it, plus 10d. I can distribute 255 equals 15d minus 45 plus 10d, or 255. 15 plus 10 is 25d minus 45. I've now just got a linear equation in standard form. My variable terms are already together, or well, I didn't even have to put them together. I only have one variable term, so I can move directly to isolating the variable term. I can do that by, I have a 2d minus 45. I want that 45 off of the 2d, so I add 45 to both sides. On the right, I have 25d. On the left, I have 255 plus 45, that is 300. And I've now isolated my variable term, and I want to isolate the variable itself by dividing both sides by my cursors and pens are being a little wonky right now. There we go. I want to divide both sides by the coefficient 25. I'll flip things around, make it d equals 300 over 25. Well, 25 goes into 100 4 times, so it goes into 300 12 times. So I think that whatever Carolyn, I think that Carolyn has 12 dimes. What would the number of nickels be then? I would take the relation n equals 3d minus 9, combined with her having 12 dimes, (36 minus 9 is 27. So I think Carolyn should have 12 dimes, 12 dimes, 27 nickels. And let me check. 12 dimes would give $1.20. 27 nickels, well, 26 nickels would give $1.30. So plus one more nickel, so that's $1.35. Add the two together, we get $2.55. And that was exactly the amount that she was supposed to have in her purse. So that checks out. So we got our answer and we checked. That does make sense. We also got reasonable answers, of course. We got, non-negative numbers for the numbers of nickels and dimes, things like that. So we have a lot of context here that we can check the reasonability against. Everything seems good. So I'm confident in this answer. Any questions on this one? This one had an extra layer of complexity in that we had to really be careful with these units. So, here we really have to think about what units is everything denominated in. How do I get everything into the same units so that I can, in a sense, kind of forget about the units from this point forward. So I didn't really talk about units again until the end here, but that was only because I took the time to get everything into the same units. In this case, we use cents on both sides. Okay, so let's work on this exercise. Let's do maybe again about 3.5 minutes or so on this one. And again, take your time, figure out what we're looking for. What are we looking for in the solution? What variables are we looking to solve for? Give them names. We can see that there are going to be two variables. So we also are going to expect two equations, two constraints. So come up with your two equations, find a way to kind of combine those down into a single equation, solve that equation, and then get the solution. So that is the process. So take again about 3.5 minutes or so for this one. This one doesn't have as much hassle with the units as up here. Uh, but yeah, take a look at this one. I don't know why my dollar signs look different between these two lines. But so if you have, if you're a little OCD like I am, sorry about that. I don't know why the dollar signs look different, but all right, take about 3.5 minutes and we'll come back and discuss the answer. Okay, let's work through this exercise. So I got most of the way through, but not quite all the way. Okay, so we have, again, the movie theater took in 1174 one Monday night, so that was its total revenue. The number of $7 child tickets was 10 more than twice the number of $9 adult tickets. How many of each were sold? So we're looking to find the number of adult tickets and number of child tickets sold. Let's call those A and C respectively. And we see from our second sentence here, the number of $7 child tickets, or C, was, or well, was is just past tense of is, right? So that's equals 10 more than, so something plus 10. 10 more than what? Twice the number of $9 adult tickets, so 2A. So the number of child tickets, C, is 2A plus 10, twice the number of adult tickets, and 10 more than that. So that was the more straightforward sentence to get an equation from. The other sentence is that the movie theater took in $1,174. That was the total revenue. Now, importantly, revenue, again, we might, if we were moving quickly and not being careful, we might be a little careless here and write something like 1174 equals A plus C or something like that. But really, the revenue is the cost of an adult ticket times the number of adult tickets sold plus the cost of a child ticket times the number of child tickets sold. Right, these cost of bits are what's carrying the unit of dollars. The number of adult tickets or number of child tickets sold, those are just unitless quantities. So if we are careful with our units, we see on the left, we have $1,174. On the right, we have $9 times A plus $7 times C. So we have everything carrying the unit of dollars. My units make sense. They're all denominated the same. I don't have to switch to cents or anything like that here. So I have 1174 equals 9A plus 7C. And if I come down here, I see that C equals 2A plus 10 can be plugged into the second equation to get 1174 equals 9A plus 7 times. Instead of C, we'll make that 2A plus 10. Make sure that 7 gets distributed to the entire parentheses, though, 2A plus 10. Or we have 1174 equals 9A plus 14A plus 70. Combining some like terms, 1174 equals 23A plus 70. Subtract 70 from both sides, 1104 equals 23A. Divide both sides by 23, and we get that A equals 48. So there were 48 adult tickets sold. And then finally, we can ask, what's the number of child tickets sold? Well, it's twice the number of adult tickets plus 10. So 2 times 48 plus 10. Or that's 96 plus 10. Or it looks like there were 106 child tickets sold. And I suppose, we probably should write a sentence here or something. There were 48 adult tickets sold and 106 child tickets sold, something like that. Any questions on this one? Okay, let's move down to this next one. This one also deals with kind of money and finance a little bit. Here, the scenario is a little bit more complicated, though, because we're dealing with interest, so we need to remember a formula. I suppose revenue is kind of a formula, like the cost per unit times the number of units, but here we're dealing with interest. So Dominic pays 7% interest on his $17,000 college loan and 12% interest on his $13,000 car loan. What average interest rate does he pay on the total $30,000? So what's the average rate? So we have interest as principal times rate times time. So this is where all of this is kind of what all of this is tying into. The principal on the college loan is $17,000. So that's the principal for the college loan. And 7% is the rate for the college loan. Let's take 1 year. Let's just take t equals 1 year. And let's see how much interest would he pay in dollars on the college loan. So what would he pay in interest? He would pay I equals, let's call it I college, equals, well, principal, 17,000, times rate, 7%. This is in dollars. This is unitless. And then times time, 1. I suppose the 7% is actually in units of per year, so that when it multiplies the time in years, those are unitless. So this combination is unitless. Let me come over here and bring up the calculator. So give me a second here to switch my screens around a little bit. Okay, so coming over to the calculator, I want to do 17,000 times 0.07, or that gives me $1,190. This is the 1 year interest paid on the college loan. Okay, now let's look at the car loan. Similar setup for the car loan. The interest for the car for 1 year is the principal, 13,000. That's in dollars. Times the rate, 12% per year. Times the time, which we're just taking to be 1 year. We're just looking at how much is paid over 1 year on both, or on each of the two loans. So coming back over to our calculator, 13,000 times 0.12. That's the point there. There we go. 1560. And that's in dollars. When I'm looking for an average interest rate, I want to take the total amount of interest he pays over, let's say, 1 year, divided by the total amount that he owes. So total annual interest is the sum of these two. 1190 plus 1560. Or what is that? 2750. So that's the total annual interest that he pays on this this debt as a whole. The total principal is 17,000 plus 13,000 is 30,000. So now I have something that is an amount of interest paid I have a total principal. I'm still taking time to be 1 year. And I see I equals P times R and T equals 1. We're just going to leave that off. I want to solve for the average interest rate. I want to solve for R. R equals I over P, the interest, the total interest over the total principal, or that's 2,750. Over here, I can just hit divided by, because I have 2,750 in my last entry here. So it'll just take that answer and divide it by 30,000. And that's 0.0917 or so. So this gives an average interest rate of about 9.17%. Something we might find interesting or perhaps a little bit confusing is if I just average these two numbers, 7% and 12%, what would I get from that? Well, oops. I'm going to be over here on the calculator. There we go. So if I do 7 plus 12, enter, and divide that by 2, I actually get 9.5. So 7% plus 12% over 2 is 9.5%. So what's going on? Why is it that if I average the interest rates directly, average the numbers 7 and 12, I get 9.5%. But when I did it this way, I got a different answer. Well, it's because our loans have different principles, right? You could imagine an extreme example. If the college loan was like $29,900 out of the 30,000 at 7%, and the car loan was like $100 at 12%, that 12% essentially has no impact. You're basically just paying 7% interest. Or the other extreme, if the car loan was like the vast majority of what you're paying on, you're going to be paying very close to 12% interest. More of your debt is at the higher rate. So this average interest rate down here takes into account the relative sizes of the debts. Now, because 17,000 and 13,000 are numbers that are kind of close to one another, right? A perfect split would be 15 and 15, so 17, 13 isn't too far off of being about the same. That's why our 9.17 isn't too far off of 9.5%. But if our 17,000 was like 29,000 and our 13,000 had gone down to 1,000, then our answer here would be much closer to 7% or vice versa. So we know that interest equals principal times rate times time. We're just kind of setting time to 1 year so that we can kind of forget about the influence that time has on this and just saying per year how much interest is being paid. Our goal is to find the average interest rate, the annual rate for this combination of loans. And that tells me I need to know the total interest I pay per year. So the combination of those two numbers. And I need to know the total principal, which is given up here, 30,000, or which we could have computed as 17,000 plus 13,000. Take that ratio, get 9.17%. Any questions on this one? Okay, so let's take a look at another exercise. I'll write down the formula again. I equals P times R times T. I equals PRT. Let's take a look at this exercise. This one's a little involved, so let's take maybe about 6 minutes or so to work through this one. And as usual, I'll wait 30, 45 seconds and then kind of jot some notes down, roughly, every minute or so, jot a few more ideas down in case you get stuck along the way or having trouble getting started. But take a good, 20, 30 seconds, read through this carefully, try to figure out what's going on, what we are trying to solve for here, what we're trying to figure out here, and then, uh, assign variables, try to get some equations set up, and then work towards solving them. But I think understanding what's going on for a situation like this, where we're dealing with money, it's a little more abstract in this sense that we're dealing with things like interest and investments and loans, a little more abstract. Um, a good bit of the work is just reading through the paragraph, maybe reading through it twice, and trying to understand what the goals are here, what piece of information are given, and so on. Okay, so we'll check back in about 6 minutes or so. Okay, let's touch base and work through the first bit of this and then finish it off. So you can see that this is a fairly complicated problem. It follows a similar strategy, a similar overall feel to the previous one, but it's a little more complex for a couple reasons. One, our interest rates aren't quite as nice, so we just have more decimal points to carry around and so on. And number two, the situation is a little bit more complex. So Vern sold his 1964 Ford Mustang for $55,000, wants to invest the money to earn him 5.2% interest per year. He'll put some of the money into Fund A that earns 2% per year, and the rest in Fund B that earns 10% per year. How much should he invest into each fund in dollars if he wants to earn 5.2% interest per year on the total? So thinking through, does it matter that it's a 1964 Ford Mustang? No, that's irrelevant information. But $55,000 is important. That's the total amount of money he has to invest. So that comes into play down here in a couple different places. We want to know how much he should invest into each fund. Let's let capital A be the amount he invests in fund capital A and capital B, the amount in fund capital B. So we know that the total A plus B has to be 55,000. If he has 55,000 to invest, he's going to split it between these two funds. So the sum of those has to be the whole 55,000. Okay, so we know we have two variables. We're looking for two equations. We got one of our equations that A plus B has to be the total amount that he has to invest, 55,000. So let's look for a second equation. Well, the second equation is that he wants to earn 5.2% interest per year. Little side note before we develop this equation. This might seem like a silly thing. You might say, well, this is kind of a dumb problem. Just put all the money into Fund B and get 10% per year. Why would you put any money into Fund A? It earns less. Why would you care about earning 5.2% per year? Like if you have more money, that's just, you can pay whatever you were planning to pay with the 5.2%, and then you have extra money left over to do whatever you want with. Well, the flip side of that is that to earn more money, to earn a higher interest rate, um, roughly speaking, you always have to take on higher risk. There are some caveats. You can do more work and you can, things like that. But if you just want an investment with a higher interest rate, a higher average return, that investment is going to have a higher inherent risk to it. The volatility, the amount that investment is likely to go up and down over, say the next 6 months or a year, a couple years, is going to be higher. So that's what, you being willing to take that additional risk is what's generating that extra reward for you, getting, say, the 10% instead of, say, the 2%, investing in maybe government bonds or something like that. That's an extremely safe investment. So you don't want to put all your money in the 2% fund because while it's extremely safe, you don't earn a lot of money and you can't afford to pay for whatever he needs to pay for with this 5.2% draw. On the other hand, you don't want to put all your money in Fund B because if you don't need that high return, if you don't need 10% per year, you're kind of taking unnecessary risk. So that's what we're looking at here. We know that he needs 5.2% per year for whatever reason, maybe to fund a retirement or something like that, whatever it may be. Hopefully you're not funding a retirement off $50,000, but whatever it is, he wants 5.2% interest. And we don't want to just put it all into Fund B because now we're taking unnecessarily high risk. And we can't put it all into Fund A because then we don't make enough money. So we want to balance the two. So that's practically speaking why you would want to solve a problem like this. It seems a little silly at first glance until you think, why would somebody be willing to pay you 10% versus 2%? And that's one of the reasons why. Okay, so we have one constraint that the total invested is A plus B, and that has to be 55,000, the total that's there to invest. And then the other constraint is that we have these two funds getting two different returns, two different interest rates per year, and we want the average interest rate per year, the average annual interest rate, to be 5.2%. So we want to not just, put some money here, some money there, and figure out what's the average interest rate, but we want to engineer this average interest rate, like from the previous problem, to be a number that we want. Right? Essentially, what we're asking is like, how much would the college loan be and the car loan be to get a total debt of 30,000 and an average interest rate of 8% or something like that. So here we're, this transitions from maybe just kind of asking a question about something that exists to engineering a situation, to saying, I have a degree of freedom here. I can decide how much to put in this fund versus that fund. How should I optimize that to get the result that I want, to get the average interest rate, 5.2%, that I desire, right? That's in a sense what engineering is, right? Manipulating variables to get the outcome that you want rather than the outcome that would maybe something like naturally arise. Okay, so let's do a similar calculation to up here. We'll take each of our two, well, in this case, they were debts, below, in the next one, they're assets, but whatever. We'll take each of our two, loans or each of our two funds, find each of their annual interest amounts, add them together to get a total annual interest. So the annual interest received from Fund A is going to be T times R. This is annual, so T equals 1 year. Or that's the principal, the amount we put into Fund A, which is just the variable A, times the rate of 0.02, 2 percentage points. What's the annual interest from Fund B? Similarly, B times 0.10. So what is the total annual interest from the combination of the two? What's going to be 0.02A plus 0.10B. That's the total annual interest, just adding these two together. That's the expression that corresponds to, for instance, this one up here that we got from adding these two together. Right, so we have a more complicated problem here, but it's related to a simpler problem. We can look back at the simpler problem for a bit of inspiration, a bit of guidance as to how to proceed. The other side of the expression relates to the total. So what is the desired total annual interest? Well, that is 5.2% on 55,000. So 55,000 times 0.052, that's the desired total annual interest. We want to match that to the actual annual interest that we will receive. That's where our second equation comes from. So this, I would probably say, I would almost certainly say that this is the most challenging equation we've set up probably this whole course. But again, kind of looking back to the previous problem that we did that was a little more straightforward, getting a little bit of inspiration from that, getting a few ideas from that, and understanding of how the structure is going to work, that makes the transition to something more complicated a little bit smoother, a little bit easier. And at this point, I have these two red boxed equations. A plus B equals 55,000, and 0.02A plus 0.1B equals 55,000 times 0.052. Now I have two variables and two equations. It seems like I am ready to proceed forward with the algebra side of things and work on figuring out what are A and B by solving these equations. I have A plus B equals $55,000. I can solve this for one variable in terms of the other, maybe by subtracting A from both sides. Get B equals 55,000 minus A. I can plug that into my start equation down here, the challenging one to set up, and I get 0.02a, that just is copied over, plus 0.1b turns into plus 0.1 times 55,000 minus a, equals, and then the other side just comes over as well, this 55,000 times 0.052. I have an awful lot of decimal points floating around here. Let me try to get rid of some of them. I multiply by 100 on both sides. The 0.02, decimal point moves 2 to the right, becomes a 2a. The 0.1 becomes a 10 times 55,000 minus a. If I multiply 0.052 by 100, that moves the decimal point 2 to the right, give me 5.2. And then if I kind of steal a factor of 10 from the 55,000, that lets me bump that decimal point one more to the right, making it 52 times 5,500. So now I've gotten rid of all of my decimal points. Is this strictly necessary? No, probably not, but I think it makes things a lot less error prone. Okay, so let's put exclamation point on this because we've done a lot of work to get there. And we'll bring it down here where we have a little more room to work. 2a plus 10 times 55,000 minus a equals 5,500 times 52. Okay, so now I have, if I look at this, I have a linear equation in one variable, in the variable a, and I can just go through my equation solving steps. I've cleared the fraction or decimals, none of those left over. I can start by simplifying the left side, distributing this 10. 2a plus 550,000, 550,000 minus 10a equals 5,500 times 52. 2a minus 10a is minus 8a. That's a little bit annoying. We might be a little worried, but remember 5,500 times 52, that could very well end up being less than 550,000. So we might get a negative on the other side as well. So we have negative 8a plus 550,000 equals 5,500 times 52. Now, certainly if I get an A that's negative, I'm not going to be too happy with that. I'm going to go back and check my work, but we will proceed forward. Just getting the negative 8a doesn't necessarily hurt anything. If we really wanted to, we could add 8a to both sides and then subtract the other direction. But here I think I'm fine with just subtracting 550,000. I have negative 8a equals, let's see what we get on the right-hand side with the calculator. So I have 5,500 times 52 minus 550,000. So I have 4 zeros after 2 5s. That looks good. Negative 264,000. Right. And so this is good. I have negative 8 times a equals negative number. That means a is going to be positive. So, right, even though I got this like negative bit here associated with a in an intermediate step, that doesn't necessarily signal a problem. Now, if I ended up with, a equals negative $20,000 or something like that, that would be problematic. But no problem because a is going to end up being positive. So a is going to be 264,000 over 8, or 33,000. So 33,000 of the $55,000 to invest should go into fund A. And then that implies that B is 55,000 minus A. So what's left over? B should be $22,000 going into fund B. So if we put $33,000 into fund A, $22,000 into fund B, we have a total investment of $55,000. And we could check this if we wanted to, that we have an average interest rate of 5.2%. So what would our average annual interest rate be for this split? It will be 33,000 times 0.02. That's the interest for fund A, plus 22,000 times, what was it, 0.1, the interest from fund B, 2,860, $2,860 per year of interest received. What's the desired interest rate? 5.2% on 55,000. Cross your fingers. And there we go. The actual interest we'll receive from this split of investments is right in line with the desired amount of interest that we want. So we've checked our answer. It all looks good. And I suppose at this point, if we wanted to be sticklers like the book always does, you can write down, whatever his name is, Vern. Vern should invest $33,000 in fund A and $22,000 in fund B. So this was definitely the most complicated problem we've done so far. A lot of the complication came from really two areas. One is really getting this starred equation here. If we hadn't done this one before, I think that would have been far too much of a jump in complexity. But since we did this one, if you had followed along, if you had worked along with me and kind of understood what was going on here, this gave a pretty strong hint to how to solve this problem here. I think that's one of the really nice things about math is the idea of mathematics in my mind is abstraction or generalization through abstraction for the purpose of generalization. So I kind of think of this like schematic of problem types, and if you just really narrowly focus, then you might be really good at solving problems that are like this one here. But if you encounter any problem that's even a little bit different from that, your ability to solve that problem basically goes to zero. So if you just drill certain problems or you really focus on certain problems and don't think about the bigger picture, knowing how to solve this problem only really helps you solve that particular problem type. But if I look back here and say, okay, because I understand how to solve this problem, if I generalize a little bit, if I understand things a little more deeply, a little more broadly, if I think a little bit more like a mathematician and say, how can I generalize from this? What would happen if, like we did when we went through here, what would happen if this 17,000 was really close to 30,000, if it was like most of the debt was the college loan? Well, then I think the answer would be really close to 7% for the average interest rate. Or what if the car loan was most of the debt? How would that change things, right? So looking at this problem more holistically means that, okay, I've learned how to solve this problem, but I also understand a little more about the surrounding problems, right? So if I encounter a problem that's a little bit off to the side, that's kind of tangentially related to that problem, I still have a pretty good idea how to approach it. And I think this is, what we should aim for. And that's hopefully what you got out of here, is that by even looking back at this problem for some inspiration or guidance, that might have given you enough to work through this really challenging problem. And, this is challenging for a couple of reasons. One, there's just a lot going on. Two, it's kind of abstract. We're talking about interest and interest rates and things like that. It's less tangible than some of the examples we've done before. And three, frankly, there's just a lot of algebra, right? There's a lot of just little details like keeping decimal points in the right place, like not, making a mistake like multiplying by 100 and bumping this decimal point 3 over instead of 2 over, making it 52 because all the other decimal points went away. So just getting rid of that decimal point or something, right? Just a lot of these little details to keep track of. Something that I didn't make mention of is that at the end here, these are sensible answers. We didn't end up with A equals negative $20,000, but we also didn't end up with A equals like $70,000, right? If he's only got 55,000 to invest, we better not be trying to invest $70,000 in one of these funds. So these are both sensible amounts to invest as well. A and B are both between 0 and 55,000. Any questions on anything we did today? All right, so when we come back, we will do this problem. When we come back on Thursday, maybe take a look at this problem if you want to screen cap it or if you want to jot it down. Try to think through how this problem would work. So here we're looking at two solutions that are different acidity by volume. And think about these questions here. This is kind of the main question that we're going to be trying to answer. But think about the first and the third question as well, more qualitatively. Okay. So maybe a little bit of prep work for next time will help this go a little more smoothly. And interestingly, this problem, the solution is actually going to look a lot like this problem, even though it seems like a completely different scenario. The algebra that we end up with, we're going to get equations that look kind of like these equations. Right. So that's what we're going to kick off next class with. We definitely don't have time in the next just 10 minutes to work through this one. So next class we'll start with this problem and then go through maybe kind of a wrap-up exercise for mixtures. It's maybe a little bit more straightforward than the last one we looked at and this first one next time. This is maybe a little more typical of a mixture problem.